Okay, welcome everyone back to us to this course. And let me just, before I get started with today's topic, let me tell you what are we still missing to be doing before the end of the course. So we will devote 2 lectures, tentatively, last 2 lectures to key dynamics in complex systems. And then we will spend the last month diving in statistical field theory, basically recovering many of the results that you might have obtained in the course of quantum field theory using path integrals, and therefore getting you acquainted to the language of using path integrals as a standard tools to derive results in field theory. In field theory, okay, field theory is a standard technique, not only in relativistic particle physics, it is used very much also in the context of statistical mechanics for reasons that I will discuss with you. Okay, and then I think we'll be more or less done with the course. Okay, so today I want to introduce the last topic that concerns the journey into rare events and complex systems, and this time is a purely statistical mechanical property, and it's the statistical mechanics of rare processes. So we have this discussion many times. Suppose you have a system which are schematized with an energy landscape like this, U of x, and with a corresponding temperature that is much smaller than the barrier. Then we've been ad nauseam now exposed to the fact that observing transition across the barrier is a very rare event. And in fact, if you have a long, suppose you're so good that you can solve the problem of sampling the system, you have a very large computational resource for this system, and you can generate a longer ergodic trajectory. Then, of course, from a longer ergodic trajectory, you can build equilibrium distributions. Well, you can do it also using the theory of the ensembles, of course. But in a way or in another, we know that the distribution is very large in the basins and is exponentially small under the barrier. And the reason is, precisely that transition pathways are extremely rare events. So in some sense, Boltzmann theory is a perfect theory to deal with equilibrium, because if you look at Boltzmann theory, it provides you a distribution that is large where the system spends most time. And in equilibrium, that's all you're really interested in. Small events, rare events, transition pathways do not contribute significantly to the Boltzmann weight by definition. So if you want to learn about how a process changes, say how some complex system goes from one state to another kinetically in time, for instance, using our standard protocol problem, how a protein folds, for instance, then clearly Boltzmann theory is not the right theory because it's exponentially insensitive to the transition paths. Okay, so you will be always dominated by the basins, and none of the equilibrium ensemble will be significantly affected by the physics you're interested in studying. So from this discussion, it is clear that we need a theory that is specific for rare events. such that somehow singles out only transition pathways and analyzes the properties of transition pathways. And we want to do that in the most rigorous way, in some sense, at the same level of theoretical rigor we have for the Boltzmann theory of equilibrium ensembles. In some sense, we want to generalize or extend the Boltzmann theory to include, to adapt it specifically for this problem. It turns out that this problem was actually solved very recently and goes under the name of transition path theory. And I would say that the years where you could say this theory was more or less formalized, I would say I would quote 2006, maybe 2008 by the time this information sort of propagates. So we're talking about 12 years ago, not a long time ago. You were already in school by far. And I was already a postdoc, actually a faculty. So we're talking about recent results. And I would like to quote a name. There are many names. Many people have contributed to it, as always, but there, in this case, I think one person was the guy who played the role of Maxwell, putting things together in a tightly organized way. There were ideas, but he had the background, he's a mathematician, had the background to formulate things in a very, very neat way. And his name is Vanden Eden. Is in NYU. Eric. Again, there are many others who sort of played a role in this game. I'm just quoting what I believe, according to my personal experience, being the most prominent member of the community who pushed forward the formalization of this theory. So, what is this theory all about? It's a theory of transition pathways. So the beauty of transition path theory, it is basically structurally and conceptually homologous to Boltzmann theories of ensembles. And the idea is basically to define three main logical steps: define the ensemble, replace time averages with phase space average, introducing distribution, and then derive results. By derived results, I mean the famous results of statistical mechanics, for instance, the Boltzmann structure, the structure of the Boltzmann distribution, and blah, blah, blah. The equivalence of the ensembles and all that. But the logical step of the Boltzmann theory, if you want, is first you define the ergodic assumption, and then you define the property of your ensemble, which is the equilibrium ensemble. Then you make a physical assumption. Then people have tried to prove it in some kind of a rigorous way, but originally it was at least a physical assumption. That is, that if I wait long enough, I can replace. I can introduce the concept of the copy of the system by replacing time averages with averages over distribution densities, right? And then I derive the distribution density. Now we can do the same from transition path theory, and the result will be surprising because we will recover some formulas that have many resemblance to those of equilibrium theory, but with corrections here and there that take into account the fact that we are looking at non-equilibrium processes. Okay. So let me start from the scratch. And to start from the scratch, let's define the transition path ensemble. So let's make some general assumptions to begin with. Now, the general theory only requires microscopic reversibility. and Markovianity in phase space. So, but we will be more practical than that in these lectures and focus on the Langevin dynamics, the overdamp Langevin dynamics, which is of course Markovian in configuration space, which is stricter condition, and obviously obeys microscopic reversibility. So we will assume our system obeys Langevin dynamics, but you don't necessarily need to do that if you want to recover basically all the results that I will discuss today, with some caveats here and there. Okay. So let's set up a system. We have a configuration space, and in configuration space we define some topologically closed hypersurfaces which are identified with two regions of configuration space that are enclosed within this hypersurface. So the hypersurface is a 3n minus 1 dimensional surface, which, as in Gauss theorem, embodies a volume of configuration space, which I will denote with R. And this stands for reactant. And then I do the same with the product, and the surface will be called with this symbol, partial R and partial P, which denotes the embodied surfaces. Okay? Now, these definitions are completely general. So I don't need these reactants and protons in principle to be associated with bases. However, of course, the whole architecture will turn out to be useful only if reactant and product are metastable states. Otherwise, there's no advantage of doing instant transition path theory, because the idea is that we are interested in whatever is in between these two. Okay. So even though the theory is more general than that, we shall assume that reactant and product basically surround basins. Two basins separated by some kind of barrier. So what do I mean by that? That the equilibrium distribution is exponentially larger inside than it is in the region outside. Okay? And in addition to this, we shall assume, without loss of generality, we can assume that and the entire system is divided, contains only two bases. Because if the system contains many bases, then we can chop off these two bases and study the transitions separately with transition path theory, and then combining all these transitions together to get the picture in the more complex environment where you have more than two bases. So limiting ourselves to a system with just two bases doesn't really shrinken the applicability of the theory. Simply it sets us in a theoretical framework that is avoiding unnecessary complication. Okay. Now, if a system consists of two basins, let's look at let's imagine, we have microscopically reversible theory. That means that we are bound to ultimately equilibrate. Okay? So let's assume computation is not a problem. And let's assume we have generated a long ergodic trajectory. What is a longer Jolly trajectory? Is a trajectory that basically visits all the relevant part of configuration space. And I really don't want to say all configuration space, because this idea of trajectory visiting all configuration space is only true in principle, is never true in practice. And that's, otherwise, since the configuration space of any realistic system is infinite practically, thermalization would always take an infinite amount of time. Okay, so when we say that a trajectory is ergodic, is that basically when we compute an average of equilibrium average of an operator over a trajectory, we have reached a regime where if we increase the time arbitrarily of my trajectory, my averages don't change. That's the concept of real ergodicity. Okay? And of course, in the presence of metastability, this concept of ergodicity, it's very dangerous. For instance, suppose I have my usual two-state system, and I look at a trajectory starting, say, from the left state. So that's -1, and that's 1. I'm tilting my x-axis 30 degrees, so that's the x-axis and that's the y-axis, okay? And actually here is time, sorry. So I start from -1 and I start wandering. And only extremely much later, I perform a transition to the other side. Okay? Because this transition is rare. Now, if I were to measure any observable, but suppose I didn't know that there is another side, another basin here, because when you do simulation, you don't know whether you have explored the entire configuration space. Of course, you know if you have a one-dimensional plot, but if you have a 10 million dimensional plot, you cannot, right? All you know is that you measure the observable for a certain amount of time. Now, you can immediately see what is the problem. Say, suppose I'm interested in measuring one observable, for example, the average position, right? Then clearly, no, after a very short transient time, maybe I'm starting from here rather than from here. After a certain time, my average will converge to -1. And then maybe after time t, I double it and I triple it and I still find -1 and I declare I converged. But who knows if I had waited one more time, the system would have gone to the other side. And the real ergodic result, of course, is average value of x is 0. So the concept of ergodicity is a fantastic concept in terms of mathematics, but it's a very difficult concept to put into practice. And basically, it only results to the magic word, let's hope. Okay? There's no way you can go around this problem. You can only be self-consistent. Okay? Okay, having said that, let's assume that this problem is not an issue in this case. And indeed, we have many back and forth trajectories, or in particular here between the reactant and the product. So how does a normal trajectory look like? Well, most of the time, the trajectory will wander, say, the reactants. Occasionally venturing outside, but most of the time returning back, because remember here, the energy barrier is very steep. So anytime you get out. But sometimes when you exit the barrier, you reach a surface, which is basically the top of the mountain, so to say, from which you have 50% probability to make it back or to go to the basin. And if you're lucky enough to cross it, then you start having chances, and there are some trajectories. The area actually are those we identified with the transition path ensemble. And if you look at it, what is the property that these trajectories, these are portions of the original ultra long ergodic trajectory obeying one specific property. They leave the reactant product surface and they cross the product surface before touching the reactant product. Right? In contrast, this trajectory here leaves the reactant product, but it does, but touches, but the next surface that it touches after leaving the reactant product is again a reactant product. And likewise, the trajectory exiting here and returning that will not belong to the transition path ensemble. So now the first step is, of course, that of putting these ideas into math. Now I'm going to throw the definition and then we're going to comment on that. But I think you got the idea. So we define two times. So given a time, we have a trajectory, and we have an ultra long trajectory, and let's t. So x of tau is my trajectory with tau going from, I don't know, 0 or so minus t to big T. This is a large time. And I have a time t in this interval. Or let's call it t half and t half. So the total time of my trajectory is t. So let's define two quantities, two functions of this time interval, of this time, this instant. T plus of t is defined as the smallest time t plus greater than my time, so the nearest time in the future, such that x of t prime belongs to R united to B. So basically, suppose at the time t, I'm in the middle of the road here. T prime is the first time after t that I reach the product surface. T negative of t is the largest time such that x t prime again belongs to R united of P. So it's the last time I was either in the reactor or in the product. Now, let's consider a reactive trajectory x of tau is said to be reactive at time t if three conditions apply. The first condition is that x of t belongs to omega tau. So what is omega tau? Is the complementary of the configuration space volume modulus the R united P regions of configuration space. In other words, I must be in between. Omega is the configuration space, R is this volume, P is this volume, and this part here is omega complementary of R united of P. Okay, so I must be in a transition region. But that's not sufficient because I can invent a trajectory that makes it there and goes back. Okay. Now, the second condition that I'm interested in is that x of t minus of t was in the reactant, and 3x of t plus of t is in the product. So in other words, the last time that I left either of the states, I was in the reactant. I was last seen in the reactant. And the next time I will go back into R united to B, to P, so I will be in any basin, I will be in the product. So with this condition, I'm clearly ruling out this orange line, and I'm back to a green line. So this is when the trajectory is said to be reactive at some specific time. And now we define a concept that is the concept of transition path. Is a piece of the ergodic trajectory xt such that is entirely reactive. So let me not put that too much into mathematical meaning. I could define a definition that mathematicians would like, right? So, but basically, let me say I have my time series of x of t. So I have t equals, say, 1, 2, 3, 4 seconds, right? And then based on the previous definition, for any point in this line, I can say if I'm reactive or not. Typically by continuity, if I'm reacting at some time, I will be there for more than just an instant. So I can draw in orange the segment where I'm continuously reactive. So these are times in which the ergodic trajectory is reactive. So if I were to draw it, something like here, 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 for instance. Here are two. I'm not considering reactive this because of this particular definition that I'm using here. But I could generalize this and make it symmetric. Since the theory is microscopically reversible, it should be robust for this generalization. I would have double statistics. But conceptually, I find it easier to remain with the idea that reactant and product are distinct, and I only look forward in time. Okay? Now, I can define a fundamental problem, fundamental concept on physical chemistry, that is the reaction rate. And the reaction rate kappa from R to P is the limit for the time interval that goes to infinity of my reactive trajectory, of the number of reactive pieces of my trajectories up to time t divided by time t. So it's basically the density of the orange lines. So basically it tells me how often, how many reactive events I have per unit time. And of course, the limit from time goes to infinity is needed because I want the system to be ergodicity. Okay? Now, The next concept I want to introduce to you is a concept that is pivotal in the entire discussion that will follow. So basically, it turns out, and you will realize this only a posteriori, that all you need in order to go from the Boltzmann theory of ensemble to the transition path theory is this particular new concept. And you will be able to define all the stochastic descriptors and distributions that characterize kinetics of reactive events in terms of the Boltzmann ensemble plus this new concept. And the new concept is called the commuter function. Now, as usual, you can define things very formally if you want to, because as you can imagine, this is a nice ground for mathematicians. However, I mean, I would like not to indulge in unnecessary formalism. And so let's just simply give an intuitive definition. So say the forward, plus means forward, commuter function is a probability that a trajectory initiated from X in configuration space, remember we are in the framework of Langevin dynamics, overdamped Langevin dynamics, will land into the product before visiting the reactant. So, and clearly the backward commuter function is the same thing, is the probability that I will land into the reactant before visiting the product. So just to visualize this, I have my reactant and state and product. Clearly, at least in R and P, this definition is trivial. The forward commuter function is 0 here because all points are already in the reactant. So at any time, they will visit the reactant before visiting the product, starting from X. And all points here, the forward commuter is 1. Now, from this point on, I will always consider the forward commuter and occasionally tell you under certain circumstances how you can get the negative commuter from the forward commuter because they're trivially related. But let me, before we go into that, let me just mention for a second only the forward commuter. So the first thing we understand is that Q plus of X restricted to this is 0 and Q plus of X restricted to the product is actually 1. However, the commuter function is, of course, a probability field, which means that you can imagine to define isocommuter hypersurfaces, and they basically represent a foliation of configuration space using the language of differential geometry, a foliation. And in each of these hypersurfaces, the commuter takes a value. For instance, here is going to be 0.1, maybe here is going to be 0.2, 0.5. This is the separatrix between the mountains. Yeah. Before here, you're more likely to make it to the reactant. This is the point of likely non-return, if you want. And then, you know, here is probably 0.9. So it is not a probability density. It's a probability field. It is always taking values between 0 and 1 everywhere in configuration space, even on regions that are likely not to be visited at equilibrium on top of some crazy mountain. Because if you start a trajectory from there, you will have a certain probability to end up in the reactant or in the product. The distribution being driven by the fact that you're subject to stochastic fluctuations. Okay? Making sense? Okay. Now, the if the system obeys Markovianity and microscopic reversibility, then clearly the probability to make it from the two trajectories obey this nice relationship, because either you make it to the reactant first or you make it to the product first. So Q minus is completely determined given Q plus. Of course, this is assuming that nothing changes during the course of time. You're not changing the energy landscape, so to say. So in particular, you're assuming not to put any extra work onto the system, so you obey macroscopic reversibility. And again, of course, you're assuming that the probability only depends on your initial condition, which means Markovianity. If also it depends on its history, then of course things would be different. But we are always working under this Now, the question we now want to solve is how to compute such a committer. Of course, you may say, I can always apply the definition. For each point in configuration space, I run many, many trajectories. And I'm happy when I have enough statistics. Say, if I'm in this point, I want to compute the commuter function in this point, I run 10,000 trajectories and count how many times I go first in one and then in the other, and then do statistics. Okay? Now, it turns out you can do better than that. It turns out that in order to you can actually demonstrate an important theorem, which is a formal one, and says, so let me say theorem, that we aim to demonstrate this theorem today. Okay? And then next lecture, we're gonna connect these results to Boltzmann ensemble and obtain the theories. So we're gonna wrap up by this week with all this, okay? So the theory we wanna state is that the committer obeys a static backward Kolmogorov equation. So in other words, the committer satisfies the differential equation, which is a partial differential equation. With boundary condition that now I'm neglecting the plus. Now, whenever I say Q now, since Q negative is trivially related to Q positive, I will remove the plus from Q plus and define Q negative as 1 minus Q. Okay? So obviously, this is the system PD that this function is satisfied. So it looks like a little bit like a conductor's electrostatics problem, right? Where you have a slightly different equation. In conductor electrostatics, you don't have this part, right? You have a Poisson equation. Suppose you have no electric charge, just a field in a condensator. You know how things were done in electrostatics, right? And then you know that the potential is constant on the surfaces of the conductors because there's no field inside the conductor, right? So you impose boundary conditions, and you do that by doing, for instance, the images method. Now you do exactly similar things in this case. It's a very similar problem. In fact, there are methods for getting analytic solutions that are essentially the same as of continuum electrostatics. But let's not worry about that. Let's stick to general formalism. Now I want to show you today this result. Okay, this part is obviously trivial. And of course, it's trivial and wrong as I wrote it. This is correct. So the idea is to define the so-called first passage time. Oh, I cannot write anymore. So in order to prove that result, we need some theoretical additional concepts. So we don't go straight into the proof. We introduce some mathematical objects, and then we use it to do the proof. Okay. And the idea is the distribution of first times. So physically, what do we want? We want, suppose you have a barrier, and then of course the first time you hit the product state, say here, is not constant over time. It depends on, it's a Poissonian distribution basically. Sometimes it occurs very quickly, otherwise it takes longer, and altogether will provide a Poisson distribution. Right now, you want to define these distributions in terms of quantity that relate to the underlying microscopic dynamics. So the way you do it, you define W as the union of reactant and product. But let's be more generous. Let's consider a general hypersurface W now in configuration space, whatever it is. I will draw it like this. And then I will define a conditional probability, PW star. And you see why star. It's the probability to go from Xi to Xf in tie t without ever touching this. So it's a probability condition to the initial condition and condition to never touch W. So for instance, this path will contribute to this probability, but this path will not contribute to that probability. So it's like you are a kid in a kindergarten and some nasty guy has put high voltage on the fence. The kids who touch the fence die. So they are free to play in the kindergarten. They basically move by random motion or whatever is their dynamics. Typically it's driven by Ninja Lego these times of the year. And whatever it is, once they touch the fence, they die because the teacher gets angry and eats them. Okay? You can get the age of my kid by this kind of example. Okay, so once you have this object under place, then you can basically define the first passage time distribution rigorously from microscopic concepts. So the first thing I want to show you is that P star obeys a Fokker-Planck equation. So basically, the star doesn't change the equation. Okay? And you should not be too much surprised, because if you think about electric field in a conductor, in the space between conductor, and the electric field in a space where there's no conductor, they both obey Poisson equation, right? The only thing that makes a difference is what happens at the surfaces of the conductor, and that will introduce non-linear dependency on the solution, of course, because boundary conditions are non-linearly affecting the solutions. Okay? So, but to see this very clearly, well, you can provide a path integral representation of P star. And it's basically the same path integral with always knew and loved at this point. But this time, besides our effective path, we introduce a new functional which I draw in a different color, where omega of x, and sorry, there's a time interval. So basically, along with the effective potential, I change it, and I say the effective Hamiltonian goes into effective Hamiltonian plus a function, omega of x, a new contribution to the effective potential, okay? And this is such that it is large, say, infinite, in the region, say, on, or even simply at dw, at 0 everywhere else. Okay? Now, what happens to a statistical path that contributes to this sum that touches the fence? Then all of a sudden, the probability of this path will pick up, even for the shortest time, a large number, arbitrarily large, infinite number. Now, if this number is such that to overcome everything else, because I chose it arbitrarily large, then the probability of this path will go to 0. But then, let's look. What is the, but from this equation, you immediately see what is the Fokker-Planck equation that this guy obeys. I define the path to be like this, and I can immediately read off the Fokker-Planck equation because it's the Fokker-Planck equation in the Hermitian form, right? It's the Fokker-Planck equation that is in the form H, say, I'm giving the Hermitian formulation here, which is as good as the other. Okay? Now, by imposing the obvious condition that the probability in x of times omega is 0, because we know that, because there, of course, I'm having the teacher very angry. Okay? We understand that this guy can be taken away because it gives you 0, right? Because of, okay, fine. To be pedantic, this is going to be e to the negative b half u x times psi of x, and then I can take this in front. And this is 0, okay? So we have proven that psi and p obey the same Fokker-Planck equation with different boundary conditions. No big deal. The next step is to define the so-called survival probability. So we have an infinitely, no, we have our kids in the break between 2 lectures, they go to the kindergarten and they are playing for a time t. They've been playing in the kindergarten for a time t in the presence of the fence right nearby. And you ask the question, what is the probability that a kid starting from position xi at some distance from the fence is still alive at time t? Remember, if the kid touches the fence, the teacher will eat it. Okay? So it's called the survival probability. And it's basically the probability to go anywhere in time t starting from x without touching the border, integrated to go anywhere. Because I don't care, it's the cumulant, right? I don't ask what is the probability to be in x at time t without having touched. I'm asking only not to have touched, so I can integrate the probability of having ended up everywhere you want. It's the cumulant, the cumulative probability. And of course, given a survival probability, you basically have all the information, because 1 minus the survival probability at time of relative to the surface dw time t starting from xi is related to the probability of crossing for the first time the surface at time t. So this is the probability of having died, of being dead at time t. And if I'm dead at time t, this can happen because I touch the fence anytime between 0 and t, right? And this is therefore the integral between 0 and t in d tau of the probability of touching the fence for the first time at time tau, right? This is the first passage time distribution. And therefore, the first passage time distribution is nothing but the time derivative of 1 minus the survival probability. And therefore, is d by dt of s d omega t xi and now you can actually compute this, because we know how to write this in terms of a Green's function. This is negative integral dx d by dt of p star w xt xi. Okay, I just applied the definition of S. Okay, now I have a time derivative, and all I want to do is to remember that this I use the Fokker-Planck equation, because I know that P obeys the Fokker-Planck equation, so I can write negative d integral dtx of the divergence of the Fokker-Planck current. Right? The Fokker-Planck equation can always be written as a continuity equation, remember? Now I have an integral of a divergence. What would you guys do? I cannot hear you.
Partial integration.
Almost. In multi-dimension, this is called the Gauss theorem, right? So I relate this to the integral over the flux of the surface. This is the elementary oriented element on the surface. Remember Gauss theorem of the current. Okay, and this is called actually, if you think about it, the first passage time distribution. Okay, now this is the proper definition of first passage time distribution. Okay, I can stop here. And then, of course, you can define mean first passage time distribution and all that. And I will not this. And the interesting in that is that the first passage time distributions and mean passage time distribution are normally easy to measure. So typically, when you want to make contact with the experiment, you compute the rates. For instance, the folding rates is something you can measure. When you say the protein folding occurs once every milliseconds to seconds or minutes. So the theoretical interest in this concept is beyond, so to say, that of a computing a committer. Is a central object in statistics. Okay. And in fact, guess who first invented all this? Gamblers at Las Vegas. They needed to know, the mathematicians, these were mathematicians paid by the hotels of Las Vegas. They needed to know how long you need to have your players to play before they run out of money. Okay? Because if your game must have an intrinsic time scales that your players run out of money before being happy with the game. Otherwise, you're driven by statistics, right? So you have to modify the rules of the game so that the mean first passage time, an average player with an average amount of money runs out of money, is more or less in the order of a few hours. Okay? So that's an interesting story. See how the gamblers actually were developing all this mathematics. Okay. Going back to us now. We want to understand the transition path time. Okay. So to understand the committer, to understand the committer now, I define W to be the union of the reactant and the product. And I apply a definition of what I'm doing now. I'm applying the bare definition of committer. If you think about it, is the flux of the Fokker-Planck current with these boundary conditions across the surface of the product. Because it's the first passage time distribution integrated over all times. So if I take this and I don't integrate it with respect to time, I say this is the probability that I cross the product the first time at time t without touching before the product or the reactant. Right? And I integrate it over all times. So I cumulate away the specific instant in which it happens. And then I say, this is just a product that I cross the product before the reactant at any time. And now basically I work the proof backwards. So basically, all I have to do from this point on is to write this in terms of the gradient of the Fokker-Planck conditional probability with absorbing boundary conditions. And now this is the Fokker-Planck operator. I can relate it now. The result that I'm now I'm going to use one more result. I want to, so let me explicitate this for a moment. Now the X that sits in the committer is in fact the initial condition of your conditional probability, because you're interested in the probability that from X I cross the border, right? Now, if you remember the spectral decomposition, you will remember from the spectral decompositions that the propagator that obeys a forward, so basically from this equation, remembering that this guy obeys a backward Kolmogorov equation, is an eigenstate of the backward Kolmogorov operator, right? It's the left eigenstate. So basically it turns out that P, with respect to X, my systems obey my standard Fokker-Planck equation with respect to final X. But with respect to X prime, so let me call T naught the initial time. If I differentiate with respect to D naught, in other words, I will get the backward Kolmogorov equation. Evaluated with respect to the initial condition. So this is a typical property of Fokker-Planck equations that simply come from the fact that on the right here, you have that your spectral decomposition is such that you have right eigenstates here and left eigenstates here. So when you act with the time derivative, you can think about the time derivative being over the time interval, t minus t naught. There's a relative time. So in other words, if you know, the by dt of t minus t naught is equal to negative d by dt naught of t minus t naught, right? So that's why there's a negative sign here. And everything else is the fact that you get a backward Kolmogorov for the left eigenstates. So considering this in mind, we can go back to here. Now we have a time interval. Sorry. Oh, pardon. We have a time integral. So we were stuck here. We have this integral in here. And now this means that this, from the equation that I just showed, that dt in p xf t x t naught can also be written as Fokker-Planck backwards with respect to x dp xf t x t naught. Where again, I flip the sign from negative to positive because this time I'm differentiating with respect to t and not t naught. And the two are related by a negative sign. Okay? But now you're done. How come? Because now I'm going to show you. Let me apply h by this quantity here. The backward Kolmogorov on the commuter. If I apply the backward Kolmogorov of the commuter, I have the backward Kolmogorov with the derivatives with respect to the initial position x, and then I have my integral, I have my flux, and I have my current, which contains as initial condition X. Okay? Then I basically copy whatever we have done to this point. I have my derivative with respect to x prime, grad u with respect to x prime, grad of the current. But now I'm moving this operator across these derivatives. So I have h dagger with respect to x of p x prime t x star. Okay, do you follow me? So what have I done? I've simply applied this here. This acts on this. But then using what we did before, we know that this equation could be written this way, where these are x primes, so act on this. Therefore, since these two derivatives, they act on these derivatives that sit in here, don't act on this function because they are different variables. So they pass through. Okay? And they arrive here. Now I use the Fokker-Planck equation with respect to this. Which basically tells me I have an integral d sigma prime. I have this derivative here. I have the integral in dt and the partial derivative of this guy. Because this is the Fokker-Planck equation. And now look, I can do this integral. Is the integral of a partial derivative, fundamental theorem of calculus. And therefore, I can say that this is a function that depends on t equals infinity minus a function that depends on t equals 0. And this function t is the first passage time distribution. So what we discovered is that if I apply the backward Kolmogorov operator on the commuter, I get a difference between the probability of performing a transition for the first time at infinity, negative the probability of performing the first time at the initial time. Now, if you're ergodic, what is the probability that the first time you touch the fence is at infinity? Are you with me, guys? You're muted. What is the probability to touch the fence for the first time at infinite time? That means, what is the probability that it takes me infinite amount of time to touch the fence for the first time, if I'm ergodic?
0.
0. Because ergodicity tells me I'm getting anywhere in a finite amount of time, right? So the first of these two is 0. The second probability is, what is the probability that I am not in the fence and I will touch the fence in no time?
0 again.
So we discover that the backward Kolmogorov equation is equal 0. Which is a fundamental, there's a fundamental insight into this, because for instance, in the simplest case of one dimension, I can use this to solve the problem, because in one dimension, this equation means 2 double second minus beta, let me say beta is equal to 1, u prime q prime equals 0, right? Then q second equals u prime q prime, which means q second divided by q prime is equal to u prime, which means that this is d by dq by d by dx. Oh, sorry. Of logarithm of q prime equals u prime, right? So I integrate both terms and I get the logarithm of q prime is u minus at x divided by q prime at x naught is equal to u of x minus u of x naught. And from here, you take the exponent and you get q prime at x is equal to q prime at x naught e to the u at x minus u at f naught. And then again, you integrate and you get a possible solution for the commuter. Okay? So this is something you can study in one-dimensional problems. In some cases, you can get a log to two-dimensional. And if you want to go to multidimensional, you have to be smart. And there's an amount of research which basically tell you how can you compute? How can you compute the commuter approximatively? And many of these algorithms are based on artificial intelligence and reinforcement learning and ideas like that. So there's quite a significant amount of research in that these days. Okay, so all this to be said, I think today I'd like to wrap up here, giving you a short summary, because we are somewhere in the middle of the crossing the river, because we have introduced this concept of commuter. Maybe you might sort of glance that is a relevant concept, maybe not. It's not completely evident from what we said so far that a commuter is any relevant at all. But we will discover that once you know the commuter, you can and you know the Boltzmann distribution of your system, then you can completely characterize all the properties of reactive events. So the theory is the commuter is a pivotal quantity, and it's also recognized to be the perfect reaction coordinate. And I will describe what I mean by that next time. So I think it's enough for today. We had a kind of a rush, and I'm ready to take questions. Okay, if there are no questions, next lecture we will define the observable state transition by theory and relate them to the commuter. And then next week we're gonna do field theory. Okay.
Just one quick thing.
Sure.
It's a doubt that I have because I've rewatched a few previous lectures, and I see that sometimes we use the symbol H daga for the backward Kolmogorov and sometimes HB, but it's not exactly the Hermitian conjugate of the Fokker-Planck operator, because there is the Laplacian of the potential missing. So it's just a question if
no. They are the same object, and I'm gonna show you why. Okay. Okay. So let's compute their Hermitian conjugate. Okay. So we all agree that H is this operator, right? And we all agree that HB is this operator. Okay. Okay, so now let's compute this and see if it's equal to HB. Okay, how do we do? Well, we take a test function, right? and we take h on psi. This is equal to integral in dx phi of x. And then, of course, I have this plus this plus this on psi. Sorry, u. Now, when I act by parts, normally, how do you try to relate this to the Hermitian conjugate? Well, basically, you act by part, right? So that at the end, you will have some operator acting on phi and then psi. And you will identify whatever is here with the Hermitian conjugate, right? Now, this is an Hermitian operator, right? We know it. Therefore, we know that when I act by part, I will get Laplacian of phi. Also, this is an Hermitian operator, right? So let me get plus Laplacian of u times phi. And psi. Now I'm left with treating by part this term here. But now when this acts on this side, it acts on this and on this. So I will pick up a negative gradient of psi, gradient of u, because the integration by part will pick up a negative sign. But I will also pick up a negative second derivative of u times psi. And the two things add. And now you got it. Yes. And of course, I forgot to put phi and psi stays. So what we discover is that this is actually HB phi psi, but we know that this by definition is H dagger.
Okay, I was missing that part. Yes, of course.
Okay, no problem.
Thank you.
So how does this course, parliamo in italiano, come l'ho trovato dal punto di vista delle difficoltà tecniche rispetto a un altro corso del gruppo di fisica teorica, diciamo rispetto a Advanced Quantum Mechanics o teoria dei campi?
Personalmente non trovo una difficoltà eccessiva o molto maggiore. C'è più una componente pesante dei path integral, naturalmente, però diciamo, li abbiamo trattati, mi sembra, in modo corretto, coerente, completo, quindi a parte magari un po' di ottica iniziale, un po' di dover capire come funzionano, poi basta, tutto fila liscio, ecco, magari riguardandosi la lezione, sì. Cioè io sono abbastanza soddisfatto.
Le critiche sono benvenute sempre e in ogni momento, quindi più che non che non mi piace sapere che gli studenti sono soddisfatti, ma sono più interessato a sapere che cosa si può migliorare. Cioè,
certo.
Nel senso, quindi vabbè, la prima cosa da capire è, insomma, rispetto a un corso standard di Quantum Field Theory 1 non trovate delle difficoltà matematiche particolarmente maggiori o particolarmente inferiori, diciamo. Più o meno siamo sullo stesso livello?
Io mi sento di dire di sì.
A livello di quantità di materiale, vi sembra tanta roba su fuoco o vi sembra normale, giusta?
Abbastanza giusta. Secondo me la parte più complicata, diciamo, del corso è il fatto che sono quasi tutti argomenti molto nuovi. Diciamo che un corso come Advanced Quantum Mechanics sono cose già viste o già sentite.
Sì.
Questo è più un corso appunto che ci sono molti concetti nuovi, proprio completamente mai sentiti, almeno dal mio punto di vista. Quindi questa è la parte più difficile, ma non per la quantità di materiale o per la difficoltà delle equazioni, insomma.
Un po' è stata dovuta alla mia scelta, nel senso che, come ho detto più di qualche volta, ho deciso di ammodernizzare il corso radicalmente. Però chiaramente se uno modernizza un corso, inevitabilmente per definizione introduce argomenti che sono nuovi. Quindi è chiaro che argomenti nuovi. La mia idea è proprio quella di introdurre qualcosa che non siano, siccome è la seconda metà del corso, che è Perturbation Theory, sono concetti molto visti da voi, che è Field Theory, rivisti in un'ottica diversa, ma sono concetti noti. Teoria delle perturbazioni, integrali, campo medio, queste cose qua. Invece in questa parte qua voglio darvi dei concetti che proprio non avete mai visto nel corso di fisica teorica e che però hanno una loro importanza. Perché quasi tutta la fisica teorica si riduce in fare l'espansione di Taylor, da cui la teoria delle perturbazioni, e fare gli integrali da gaussiani, se ci pensate, ovvero l'oscillatore armonico. Togliete queste due cose qua, e vi resta il principio variazionale, fondamentalmente. Però le idee base della fisica, le vedrete quando faremo integrali sui campi, alla fine la teoria dei campi esiste perché sappiamo fare integrali path integral sui campi gaussiani. Se non lo sapessimo fare non esisterebbe la teoria dei campi. Cioè, sarebbe un oggetto matematico inutile. Invece in questa parte qua ci sono strutture e concetti totalmente nuovi e sono d'accordo. Sì. Diciamo, se questo è il vostro principale problema che ci può stare, vuol dire che sono abbastanza contento di come sta venendo. Sono un po' preoccupato del fatto che siete pochi rispetto agli altri anni, per quello ve lo chiedo. Gli altri anni eravamo di più, eravamo una 10-13 a lezione. Vedere 3 studenti al mio corso è una cosa che non mi è mai capitata. Non so se sia dovuta al Covid o al fatto che ho le lezioni online, quindi in qualche modo uno se le guarda con calma quando vuole, o a qualche mancato gradimento del corso dovuto a qualcosa che sto sbagliando, fondamentalmente. No? Comunque, se avete feedback di qualche tipo dagli studenti, dai vostri colleghi che magari vi hanno detto che non seguono il corso per qualche ragione, incoraggiatemeli, se vi va, a farmeli avere direttamente da loro o in qualsiasi forma ritengono opportuna o dentro il blog, perché io voglio capire se ho esagerato con la radicalizzazione nel modernamento, che la gente però, vabbè, quello ci può stare, o se è una fluttuazione o se è dovuta alle lezioni in remoto o da fattori contingenti, diciamo. Ecco. Va bene, con questo direi che possiamo chiudere la lezione di oggi e ci vediamo dopodomani.
Grazie, arrivederci professore.
Grazie, arrivederci.